I will switch over to the next speaker. Hold on a second. Okay, so while the next speaker is coming on screen, I will introduce him. It's Johannes Zettler from LayTec. Quickly about him. So in 2010, he got his master's in physics from Humboldt Uni Berlin and Fraunhofer IPMS in Dresden. Then in 2015, he got his PhD in physics, again from Humboldt Uni. And while his work was conducted at Paul Drude Institute about GaN nanowire ensembles in MBE. Then in 2015, he joined LayTec in a full-time position, and he's now Senior Concept Development Engineer and CDO of LayTec, and he's the lead engineer on, or he has been the lead engineer in the EpiX development, among others, and this is also what he's going to talk about today. So he's going to give an update on LayTec's EpiX wafer mapping metrology systems. Hannes, the floor is yours.
Thank you, Christian. Thank you for giving me the opportunity to present the progress we've made with the EpiX team on our mapping station recently to a wider audience. I will start just briefly showing you how the mapping station fits in our product portfolio, and then go into more detail about the mapping station and our recent progress. LayTec's business is to provide an integrated metrology for various applications, industries, and markets. We started with providing metrology for LEDs as they're used in automotive lighting and many other places. Our metrology is used for laser production, used, for example, in machining or in 3D sensing. We develop metrology for photovoltaics for the production of solar cells, for functional glass, as it is used in tinted windows in recent aircraft, for example, or in buildings, or for power devices like those we like to carry around in our pockets and on our wrists. If you, depending on the fabrication method of these devices, we integrate our metrology either in situ, as in our home base MOCVD, where we monitor directly monitor the growth of the devices, and another similarly we do it in MBE, ALD, sputtering, PECVD. For other applications, it is not possible, or for other fabrication methods, it is not possible to in situ monitor the growth, but we can only do it after certain growth steps, and then we integrate inline into the process of production on large conveyors or in roll-to-roll systems, or also in vacuum chambers. Our tools do not only measure, but they also provide the analysis software to derive the key parameters from the measurements, as we've seen today already, like temperature, precise temperature, or growth rates. In order to do so, we have a software package that includes the material database that has not only optical properties of many materials, but also optical properties of these materials at high temperature, which is required to obtain exact results. And one of the newest members to our product portfolio is a mapping station, which then is a standalone tool to do post-process of samples after their actual growth. Now let's look into more detail on the EpiX metrology station. Inside this cabinet is an automated XY mapping stage. In that, single wafers can be loaded for uniformity analysis. We measure white light reflectance, photoluminescence, and with analysis options, one can then control the key parameters and do quality control of them. And in the end, this helps to improve the yield and optimize the target devices like Vixel lasers. As we've seen in the previous talk already, the best another benefit from the EpiX comes if you combine it with in-situ data. So in the typical process, you start in your MOCVD chamber at T0 with inserting a substrate, and while then the growth process is done in the MOCVD chamber, we can, with our in-situ tools, follow this growth process over time, or in view of the device, in depth of the device. With a spectral in-situ add-on, the Vixel add-on, we can at any given time measure a spectrum, a white light reflectance spectrum, and for any wavelengths, we can look at the transient over time. If one then wants to additionally get the 2D picture of the wafer on its spatial homogeneity, EpiX is the tool to use and to gain the most benefit when combining all of that. For time reasons, I was asked to skip the 2 slides on the in-situ add-on, the Vixel add-on. We've shown that before, and it has been shown in the previous talk a little as well. So let's use as much of the time we have to actually concentrate on the EpiX mapping station. So the mapping station is this cabinet with a footprint of about 1 by 1 meter. It's an enclosed mapping station with a touch panel on front for control. And inside the mapping station then is the actual hardware. The station itself is a class 1 laser product, so the user under normal operation is never exposed to laser light. Inside is the XY stage with a measurement head and the sample holder and other components that I will explain in detail in a bit. We have now finished the 2nd generation of EpiX. The talk from the FBH, they work with the 1st generation, and we now have improved the hardware. So we have now an extended spectral range from 500 to 2000 nanometers. The spectral resolution can go down to 0.1 nanometers. We have an adjustable set compensation to compensate for varying sample thicknesses. We allow to choose from up to 4 configurable laser wavelengths for photoluminescence. The lasers are equipped with adjustable power levels and internal monitoring to stabilize their power. The overall design of EpiX is modular, and so such that single components can easily be replaced by comparable components with to provide new functionalities. And in addition, we have a set of predefined and customized algorithms that come with the EpiX. So let's look at the interior in detail. We have the XY mapping stage, and on top of it, the sample holder, which holds wafers up to 200 millimeters in diameter, or 8-inch. And in addition, there is spots for up to 4 reference samples. The sample holder is equipped with a vacuum chuck that holds any sample or fragment of a sample in place during movement. In addition, there's a Z adjustment unit for the thickness compensation. On this Z adjustment axis, the measurement head is mounted. The measurement head has integrated all the optical components necessary to measure photoluminescence and white light reflectance without having to do any mechanical alternations in between runs. and attached to it is a distance sensor for the Z adjustment. Beneath the actual XY stage are the controllers, where we have the white light reflectance controller with the tungsten or a tungsten lamp, and the PL controller with the chosen PL lasers. For demo purposes, we shot a short video showing you how the EpiX moves. This is slowed down a little for you to show for it to be more clearer. The EpiX starts with doing the direct measurements, then does a height adjustment for the reference sample, measures the reference sample, measures the sample center, does a height adjustment for the sample center, and then starts to, does look a little pixely on my side. I don't know how you see it, probably even worse. And then starts to do the line scans. Once the scan is done, we end up with the measured data. For white light reflectance measurement, we get normalized reflectance. And for each of the tens to hundreds of thousands of spots, depending on the picture that we choose, we obtain one spectrum. The spectrum is seen here on the bottom right. And for the cursor that is here, this vertical cursor, we see then a 2D color plot representation for the wavelengths defined by this cursor. So for the wavelengths here, it's roughly 860 nanometers. We see in X and in Y the color plot, and the intensity of the reflectance is color-coded as shown on the legend on the top right, which is simultaneously a histogram. The crosshairs on the other side that you see here define on the one hand side the spectrum that you see, so you can put the crosshairs to any positions, and the cutting lines are shown here as X and Y profiles of this crosshair. So this is a normalized data, but in the end we want to have analyze the spectrum with an analysis that is suitable for this as a Vixel wafer, so we use the Vixel analysis. This Andre has shown already, so I will skip the details about it. We can measure the Vixel parameters, and all of the parameters will be then derived for each point of the wafer. And for each parameter, then again, a 2D color representation simultaneously to the raw data is generated. So here we have the cavity dip center, and we see how the cavity dip center varies over the growth. We have again over the wafer. We have again the crosshairs that define the X and Y profiles as shown here. And then there's additional statistics. If we measure photoluminescence, the procedure is pretty much the same, only we now have intensity in units of counts that we measure. So there is the measurement, the spectrum, the 2D color representation of the chosen wavelength, and the X and Y profiles of the crosshairs. For PL, you usually want to analyze the peaks. We can do that analytically or numerically using Gaussian or Lorentzian peaks, and we'll then output height, center, and width of all the peaks, area, and asymmetry. And again, for each result, 2D color representations, X and Y profiles, and statistics are obtained. If one wants to go a little further with the analysis, in all analysis, one can define spec parameters for each analysis parameter. And these spec parameters can then be used for pass-fail classification of the wafer in 2D. This is then here shown in green and red. And these results can be exported as XML files, as ASCII exports, as all the data can be exported. And if we want to go even further, we can apply virtual die pattern assignment onto the wafer. So we define by an XML structure or using the UI the dye pattern which we want to later on dice the wafer into, and virtually overlay that on top of our measurement. And then the analysis of the properties and of the 2D path-fail classification can not only be done on wafer level, but also on dye level. Now where we've seen how the results software-wise look, we can go a little step back and look again at the hardware of the second generation EpiX. Second generation EpiX comes with up to 4 configurable gratings in the spectrograph. The default setup is 100, 300, 600, and 1200 lines per millimeter. This gives us the option to choose a large spectral range and measure at one shot a large spectral range, or to measure with high spectral resolution. So in an example here, we measured the same Vixel structure with 100 lines per millimeter grading, and we're able to measure in the spectral range from 500 to 1100 nanometers in one shot. But if one is interested only in the stop band region, maybe the 300 lines per millimeter grading would be better suited. And when one gets a better spectral resolution already, we see here that the dip is much deeper than in this measurement. This is only caused by the spectral resolution. And for the PL then of the luminescence itself, one can even go even higher and use a 1200 lines per millimeter grading and have a resolution of about 0.1 nanometer. Another application example is how we can vary the pitch depending on our needs. If we want to do rapid screening of wafers, we can measure at low pitches and have measurements and results within under 2 minutes. Then a wafer is quickly scanned at high pitches. The automated analysis recipes will automatically calculate the analysis that are predefined, and results are then quickly obtained. On the other hand side, if one wants to investigate a wafer in higher detail, one can choose a pitch down to 0.1 millimeters and measure the wafers at really high detail and look at smaller areas in high detail. We've also started to do a performance benchmark where we measured samples with our EpiX tool, and a partner measured them with an state-of-the-art mapping station from an established competitor. We show here the results of peak wavelength of for PL measurements, where we used similar but not yet identical measurement parameters. But to quote the partner, we do not have to hide in terms of performance in comparison to the established competitor. Let's go into the other analysis that are part of the default package. And sometimes when one has a Vixel or any other structure, one is maybe not so interested in the stop band, but how does maybe some side lobe behave, and wants to track how that is, how uniform is that position over the wafer. And for that, we have an extrema tracking analysis that can monitor any arbitrary extremum position and track the drift of these and extrema positions and intensities across the wafer. This can be used in many different applications. We have a single layer analysis that use LayTec's material database I mentioned earlier to determine the thickness of single layers. And we also have advanced options for 2D and multi-layer thicknesses or composition fits available. Another application is the chromaticity calculation, where we can measure or determine the CIA chromaticity color coordinates from reflectance or luminescence measurements. The multi-peak fit I mentioned already briefly, but in the beginning we showed it only with one peak. Here I want to show you that we're also able to superposition multiple peaks into one spectrum and then fit the superposition of both to the measured of all of those to the measured spectrum. The results are then peak height, center, and width of all the individual contributing peaks. These can be Lorentzian or Gaussians. Sometimes, however, one is not so much interested in the individual contributions, but rather in the shape or in the properties of the overall peak. But this is asymmetric and cannot be fitted by a single peak. There, the numerical analysis comes into play, which analyzes spectrum numerically. It also gives out peak height, center, width, and in addition, asymmetry and area. And if peaks are well separated, it can also handle multi-peaks. Let's come to an example where we want to demonstrate the synergies of in-situ and ex-situ analysis. This is a dBr structure that was measured in EpiX. And when we look at the spectrum, we see that for a simple dBr, just 25 gallium arsenide, aluminum arsenide pairs, we see an asymmetric spectrum. And theory would expect that the higher wavelength site would be comparable to the lower, so the minimum would go down to 0. We then looked at the in-situ data, and the in-situ data pointed us towards the assumption that for this specific system, the growth rate was not quite constant over the long growth time of the dBr. It changed by about 1%. If we took this 1% of growth rate drift into the model, we saw that now we had a very good agreement between the analytical model and the measured spectrum. And this we fed back into EpiX. So we then fitted the 2D EpiX measurement of the entire wafer with this model, and we're able to fit the growth rate of this individual gallium arsenides and aluminum arsenides layers. And we saw that the aluminum arsenide layer, we had a center to edge variation of 2% and start to end growth rate drift of 1%. And for the gallium arsenide layers, we had a center to edge variation of 1% and a start to growth rate variation of 1%. So by synergizing ex-situ and in-situ analysis, we facilitated the correlation of the inhomogeneities that we saw in the EpiX to the actual growth parameters. And then coming back to the picture we had before, where we want to synergize in-situ and ex-situ data to get a 3D picture of the growth process, this is what we were able to do here. Let me conclude and summarize what I've shown you. We have developed a second generation EpiX with modular design for customization. We integrated four lasers for PL measurements and white reflectance. We now can achieve a resolution down to 0.1 nanometer, while at the same time being able to measure in a extended wavelength range from 500 to 2000 nanometers. Typical wafer scan times at 1 millimeter pitch are below 4.5 minutes. At 0.1 millimeters, so really high resolutions, where we get gigabytes of data in the end in less than 4 hours. The combination of in-situ data and ex-situ data allows for spatial analysis of growth rates, thicknesses, etc. And we're happy to discuss with you further analysis algorithms upon request. I want to thank our partners at Jenoptik and Ferdinand Braun Institute for the joint improvement of EpiX, and all my colleagues at LayTec, and especially the EpiX team. Thank you.
Thank you, Hannes. Okay, we do have questions from the audience. Actually, there were 2 questions which you just answered with your last slide. So we're done with those about the scan rate. Another question was by Michael Knoll, and that was about the integration of curvature measurements in the EpiX station. So if it is possible to create a full curve map of the wafer in that station in principle and as of today.
In principle, yes. As of today, not yet. It's something that is on the roadmap and that is in the design, thought of and prepared, but not yet implemented.
Okay, thank you. And then there was another question. If you could go back to that competitor comparison, please. There was the question about these features at the edge of the wafers on the left-hand side, which appear quite different on the right-hand side. Can you comment on that? What's the
You mean this area? Well, probably this area. There's a few things that we see here. Let me start with the bottom features down here. You see on the competitor side, this is quite, not smooth. On our side, it's much smoother. The reason for that, we assume, is that the competitor does not measure in XY as we do, but in our phi. However, the data is always exported in XY coordinates, so it's not measured exact at the point where the output is, and that can lead to something like these artifacts. As we measure in XY, the representation is more exact. The other point that one sees here is the higher color contrast of the competitor scale in comparison to ours. When one looks into detail, I don't know if I can do this here. Yes, I can. Is that here it's more digital. With it's less digital. So this might be details on how the peak wavelength is actually derived. We see that there is definitely some smoothing done before the algorithm, but we don't know the details of how this peak algorithm is done. In our numerical peak analysis, which we used here for comparison, we have the option how to determine the maximum, use the absolute maximum, use the mean in this 90% area, or fit a parabola. For us, a parabola is most stable and leads to the smooth, physically, logic results that we obtain here, but I don't know as precisely how it is done in the other hand side. I hope that answers the question.
I guess so. Thank you very much.